Hello dear students, welcome to the 8-week online module on digital electronics and its applications organized by Department of Electronics and Telecommunication. Students, in this week we are discussing about the topic assembly language and programming using 8086. Inside this unit we have discussed about the different address modes, what is meant by assembly language programming and all these things. In previous lecture we were started our discussion with instruction set. So we have completed the first two instructions, data transfer instruction and arithmetic instructions. Now we'll start our discussion with the logical instructions. So the next instruction set is a logical instruction set. So first logical instruction is a AND instruction. We already know what is meant by logical operation. So here the logical operations are performed by this logical instructions. So first is a AND instruction. So AND instruction, the first operand is register or memory and second operand is a register or memory. We can combine these two operands as we can take both operands as a register, one operand as register and memory. First operand is memory or register. We cannot use both operand as a memory locations. So what is happened here when we execute this instruction AND? So we'll take this example first. So suppose the register contents of this, we'll take this as a BX register and suppose this is AX register. So contents of this BX are ANDed with the AX and the result is stored in the first operand location, that is BX location. So similar operation occurs for this these two examples also. Here we are using the memory location. We can use this AND instruction for register as a or memory as a first operand, and the second operand can be taken as the immediate data. So we can directly multiply the contents of register and memory with the immediate data and the result will be stored in the given register. So here suppose we will take a register BX ANDed with data, suppose 0A hex value. So the result will be stored in BX register. So in this way the operation occurs. The immediate data can be 8-bit data or 16-bit data. Whenever we are using this instruction on 8-bit data, we have to use 8-bit register, and whenever we are using 16-bit data, we have to use 16-bit register. Next logical instruction is a AND OR instruction. So in OR operation, similar as a AND operation, first operand may be register or memory, second operand may be register or memory. We cannot combine memory and memory as a first and second operand. So what is done here, the contents of register 2 are ORed with contents of register 1 and the result is stored in first operand location. So similar happens with the other examples also. We can use immediate data also. We can multiply the register, we can OR the value of register and data and the result will be stored in the register, or we can use the OR operation on memory and data. So the contents of memory and data are ORed and this answer or result is stored in the operand memory location. So we can use here the data can be a 8-bit data or 16-bit data. We have to choose the register or memory according to the given data. So we can operate this on operate this OR instruction on immediate data of 8-bit or 16-bit also. Next is the XOR. The XOR instruction is used for the XOR operation, logical XOR operation. This XOR can also be used for binary addition also. So here in similar way the XOR operation, the first operand is a register or memory and second operand is also register or memory. Here the contents of register 2 are XORed with contents of register 1 and the result is stored here in the register 2. The same happens with the register 2, register 1, register or memory and memory or register. Now we can use the immediate data also. The XOR operation can be used with immediate data with register or memory location. The data might be 8-bit data. If it is 8-bit data, we have to choose a register of size 8-bit, and if it is a 16-bit data, we have to choose the register of 16-bit. Next is a test operation. This test operation also works same. The first and second operand may be register or memory. It can also work on immediate data, and the immediate data can be 8-bit or 16-bit. Other operation is same as the ANDing. So here what is the difference? The By testing this two registers, this ANDing is done and the flags are modified here. So modification of flags takes place in each result. So the result is considered as a modification of flags, and by checking the flag values, we can use this in some decision making statements. So here the next logical instruction is a shift SHR, that is shift R right, and the next is SHL, that is shift L. So we'll see this one by one. So shift R, we will use operand here, a single operand operation, register or memory. So we can use like this: SH register 1 or SH register comma CL. So what is done here? So we can rotate the contents of given register or given memory location through a carry flag. So what is done here? So consider 8-bit data or register, or 16-bit data or register. So this is our least significant digit, and this is our most significant digit. When we use this instruction shift right, so this content are shifted towards right. So what happens to this least significant digit? So this least significant digit is transferred to the carry flag. So this operation occurs here, and B1 goes to B0, B2 goes to B1. Likewise, each bit value is shifted towards right, and at the most significant digit, the 0 is added. So this remains empty after shifting this B7 to B6 position. So this added with 0. The same happens with the 16-bit register also. The least significant digit, it's transferred to carry flag. All the other digits are rotated or shifted towards right, and the 0 is entered in the most significant digit. Same operation occurs for the shift L. Here instead of right shifting, we are using left shifting. So we can use shift left register comma 1 or SAL comma register comma 1. So both are equivalent. SHL register 1 or SAL register 1, both instructions are same. So what happens here? The most significant bit, all the bits are shifted towards left. So most significant bit is transferred to the carry flag, and other bits are transferred to the one bit to the left of their value, and the 0 is entered in the least significant bit value. So the same operation occurs for 8-bit register or memory, or 16-bit register or memory. Next is RCR. So rotate through carry right, and RCL rotate through carry left. So what is the difference between shift and rotate? In shift register, the one bit goes to the carry flag, okay, and the carry flag values are updated. But here in rotate instruction, what happens? The least significant bit is forwarded to carry. So before this, the carry flag contents are copied to the most significant bit. So here each value is shifted to the right by one bit, and the carry flag goes to the most significant bit, and the least significant bit goes to the carry flag. So this operation is same as shift operation, but this operation or this process is new here. So in the rotation, the contents are rotated. So if we rotate this register by 8 values, then the contents of this register becomes as it was the at the start of the operation. So the same can be used for the 16-bit register or memory address rotation. So here the contents, when we shift the contents 16 times, the contents after at the end of 16th instruction execution will be same as original. Next instruction is rotate through carry to the left. So this is a right left rotation. So what happens here, the contents are rotated. Now the carry flag goes to the least significant digit and the contents are shifted one bit to the left value, and the most significant digit goes to the carry flag. The same operation occurs for 16-bit also. Now this rotate R, rotate L, or shift R and shift L can be used for multiplication also. So when we use when we multiply the given number by suppose 10, so we have to shift the number by 2 digits. When we multiply by 100, we have to multiply shift it by 2 digits, 3 digits, and when we multiply by 1000x, then we have to shift the contents by 4 digits. So likewise we can use this shift and rotate instruction for our multiplication also. Next instruction set is the string manipulation instruction set. So in string manipulations, what is mean by string, first we'll see. So string is nothing but it is a sequence of bytes or words. So in 8086 we have to operate we have to perform different operations on the string, like we have to move the string, we have to compare the string, we have to scan the string, we have to load the data in the string, and we have to store some values in the string. So these operations can be performed with string manipulation instructions. Now there is one instruction REP. So this instruction is used to repeat the execution of all the string instructions given here. So string instructions are same as the arithmetic or logical instruction we have used before, but it ends with letter S or SB or SW. So S represents here a string, SB represents a string byte, single byte, and SW represents a string word. So the offset and effective addresses of the source operand are stored in the SI register, as we have already discussed, and destination operand is stored in the DI register. Now depending upon the status of the direction flag, source index and destination index registers are automatically updated. So if the direction flag is 0, then source index and destination index are incremented by 1 for byte instruction, and they are incremented by 2 for the word instruction. If the direction flag is 1, then source index and destination index are decremented by 1 for byte instruction and decremented by 2 for word instruction. Now we'll see these string manipulation instructions one by one. So first instruction is REP, that is repeat. So we can use this instruction with some condition. Here REPZ or REPE. REPZ means repeat if 0 flag is set, or REPE, both are equal. So repeat the instruction if they are equal to, means they compare the counter register. So this repeat CMPS or SCAS, that is compare string or scan string until 0 flag is 0, means when this 0 flag is set to 1, 0 flag becomes 1, the repeat operation is stopped and it comes out of the loop. The same can be used for REPNZ. If it is not equal to 0, means until the 0 flag is 1, we have to repeat the instruction, and if when 0 flag becomes 0, then we have to stop the repetition of the loop. Next instruction, move instruction. We have already discussed this move instruction with the data operands. So here for string operands we use moves, that is move S. Okay, so S letter here shows that it is a string instruction. not a data instruction. So we can use this as a move SB, that is move string byte, or move SW, that is move string word. So we have already discussed how to calculate the memory address. As it is a string operation, the memory address is calculated with the help of multiplying the data segment register by 16 and adding to the source, adding the source index. So this will calculate the source address, and the destination address is calculated with the help of extra segment register multiplied by 16 and adding the destination index value to it. So contents of the memory address are moved to the contents of memory address E, that is destination. So the source memory location contents are transferred to the extra segment memory location address here. So by this operation, with this operation, the data segment, destination index and source index are modified or updated if the depending upon the status of the flag register, that is DF value. So direction flag is 0, then a destination index is source index are incremented by 1, and if the destination DF flag is 1, then destination and source index are decremented by 1. So the same operation occurs for move SW, that is used for string word, and this is move SB is used for string byte. So when we use this instruction, the addresses are calculated as this. Now the contents of memory address MA are copied to the destination address MAE, and the contents of source address MAE plus 1 are copied to the contents of destination address MAE plus 1. The depending upon the direction flag status, if DF is 0, then destination index, source index are incremented by 2, and if the DF is 1, then destination index and source index are decremented by 2. Next is compare string instruction. So CMPS, here we can compare the string byte or string word. So similarly, we have to here calculate the source index, source address and destination address. As we have calculated before. Now compare string byte instruction, what it does, it subtracts the location contents of source subtracts the contents of destination from the source. Now depending upon the result of this subtraction, the carry flags are modified as we have seen in the compare instruction. So if they are equal, the 0 flag is set to 1. If the source is greater than destination, then all flags are 0. If source is less than destination value, then carry flag is set to 1, that is borrow is generated, and sign flag set to 1 because answer is negative. And same happens with the compare SW, that is for word instruction. And the depending upon the status of the direction flag, if it is 0, then there is an increment, and if it is 1, then there is a decrement of decrement in the destination and source index. So if for byte operation the increment or decrement is by 1, and for word operation the increment or decrement is by 2. Next instruction is a scan instruction. So it scans the string. So SCA SB, that is used for scanning the byte of the string, and SCA SW is used for scanning the word. Next instruction is a load string instruction. Nothing but the syntax for this is LODSB, LODS. So this load instruction loads the data to the particular register. So this we can use this instruction or byte or on the word. So load SB is used to load the byte of the string, and load SW is used to load the word of the string. So here the memory address is calculated with the help of data segment register and source index register. Now the content of this stack are loaded to the register AL. This is the default register AL. If direction flag is 0, then source index is incremented by 1, and if the direction flag is 1, then source index is decremented by 1. For load SW, that is load string word instruction, we calculate the memory address as shown before, and the contents of this register, the contents of this memory location, the MA is moved to the higher bit, that is AH, and MA plus 1 is moved to the lower bit. So this is moved to the AH and this is moved to the AL. So the contents of these two memory locations are moved to the AX register. So the depending upon the status of the direction flag, if it is a 0, then source index is incremented to by 1, and if it is 1, then source index is decremented by 2. Next, the opposite of load is nothing but store. So the store S used to store the string. So store string byte or store string word. So we can use this instruction on byte or word. So memory address of destination is calculated here. So we are going to load the data, we are going to store the data in the register to the given memory location. So memory address of destination is calculated with the help of this extra segment register multiplied by 16 and adding to the destination index value, and the contents of AL are moved to the register MA. Same operation occurs for word also. The contents of AX, that is AH, is moved to the MAE, and AL is moved to the MAE plus 1, and depending upon the status of direction flag, the source and destination index are incremented or decremented. So in this lecture we have discussed about the logical instructions and string manipulation instructions. In next video we are going to discuss about some process control instructions and assembler directives. Thank you.